So if we have a circuit, a wire is just something that moves electrons to go down a potential. So this is how we draw a circuit.
A circuit was, wait, what did you say?
I'll get to it. I'll get back to it again in a second. I need to read it right. We have an epsilon, which represents an electric potential difference. Great. Another use of epsilon: electric permittivity and electric potential difference.
Is that a capacitor or battery?
So it's measured in volts. This is a battery. This is a power source.
Okay.
Yeah, we have to draw one that's shorter than the other.
Yeah. Sorry.
Because when they're equal.
Okay. Right. Sorry. So the two lengths being different represent a battery, and the two lengths being the same represent a capacitor. So this has an electric potential difference, and the wire is just a thing that allows electrons to flow from the
current
negative voltage to a positive voltage.
That's the flow of electrons, right?
The flow of electrons.
But the current is opposite of that, right?
Right, exactly.
Yeah.
I'll do a second.
It's so confusing.
Yeah, so electrons go from negative to positive because, if we have negative volts and we have positive volts, like just as we learned with all of electrostatics, they're going to want to go towards the positive voltage. The wire just is a medium for them to do that. They don't want to jump off and fly in the air because it's easier to go through the wire. The wire has a lower or a higher, one of the two, electric permittivity for the electrons to go through.
Yeah.
That's why they choose the wire.
They can't go through the battery because there's like the
Yeah,
solution.
right, there's stuff in between the battery that doesn't allow them to jump. So wire is just a path. The electric field, if you draw it around like a battery, is going to look like a dipole. The same way that we had an electric dipole. And the wires could be pointing somewhat in the direction of that dipole electric field, like here, this way. The electric field's this way, but the best they can do is this way in the wire. So they're always going to follow the wire. Yeah. Okay. So first we have flow of charge, which is called current. Current is equal to dq dt. It's the change of charge over change in time. But first of all, we're going to inspect what a little bit of wire really looks like and what that means for the current. So let's say we have a chunk of wire here. There's a bunch of, I'll bring this over here. There's a bunch of electrons in this chunk of wire. I'll actually use a different color. And let's choose a little bit of volume of the wire. Just the volume of the wire. Actually, let's just make it a square. So we're going to call this dV, a little bit of volume of the wire. And dV is equal to A dx. The wire has a cross-sectional area, and this little width we call dx. Okay. We're also going to assign a variable called n, which is the amount of what's called carriers per volume. So this is the carrier density. N is the carrier charge density. So we call all these little dots, these electrons, carriers. They could actually be anything. If we had a bunch of like little double protons, like I guess hydrogen atoms, they could be carriers in a wire, but they're not. We always use electrons for carriers. Raja, I can pause for you if you want.
Oh no, that's good.
Okay. I will. Not to pressure you to go from, it's okay. No phone allowed in physics lecture class. Okay. So we have N is carriers per volume. I guess this is just V. So our carriers here are the electrons. And then we have Q, so the charge of a carrier. In this case, it's -1 E. Nice, okay. You can do that. This wire has a charge density, rho, and that is equal to the carrier density times the charge. And that's because, you know, if we have the number of carriers times the charge per carrier, I guess we'll just use Q per carrier. Charge per carrier times carriers per volume is equal to charge per volume. That's why we have that. And then we have rho is equal to dV dQ. Sorry, dQ dV. And that means if we multiply dV with rho, we get rho times dV equals dQ, and that's equal to nq. What? Wait, does that make sense? Alright, that makes more sense. Okay. A little amount of charge is equal to the density times the little dV. Yeah. So what I'm getting at here is I'm using these formulas to derive like how much carrying current there is based on the size of the wire. So the next step is to put it all with respect to T. So first of all, we can change dV to be equal to AdX, which we determined over here. nqA dx. So a carrier charge density times the charge per carrier times the area times the little bit of x along the wire is equal to the amount of charge. A little amount of charge. And if we divide both sides by dt, we get dq to t, which is equal to current, is equal to nqA dx over dt.
dx over dt, that's
Yeah,
velocity.
that's velocity.
Oh.
So, current is equal to carrier density times charge per carrier times area times velocity of the carriers. So this is sort of like how we express
How do you tell which V is which?
which what?
Voltage versus velocity.
Velocity is usually lowercase. And
Okay.
voltage is usually uppercase, but it's also in context. So you can use this formula if you have a bunch of moving charges. That's the amount of current that those charges are charging. And that's also just equal to rho. Rho is equal to nq, so rho times area times velocity of the carriers, or rho times area is also equal to charge times velocity divided by the window of that is what we're measuring. Sorry. Okay. The total amount of charge in this window times the velocity of the charges divided by the size of the window is equal to the current. And that sort of makes sense. That's like, you can also say that Q times Q times delta X, that's like linear charge density times velocity. These formulas are all equal to current. So I recommend you write down this, and then you write down like this, and maybe this. what I was trying to get at here is like all these formulas make intuitive sense. Like if we have a little bit of charge, and that little bit of charge is moving with velocity, and we have to divide out like the size of the charge, it's like how much current. Because like I guess if you double the size, then that also doubles the charge. That's why we have to do a ratio here. The velocity is like sort of representative of how much charge is piercing like some surface a long time. It's really amount of piercing like charge velocities that demonstrates like how much current is going through something. Yeah, but it's just back to dq/dt.
Okay, wait, sorry if this is a little stupid, but N is the amount of carriers in the entire wire? Or in just the window?
Carriers. It's just a volume. It doesn't matter, but we multiply it by dB.
Oh, anyway, yeah, okay.
So yeah.
Oh, yeah.
It's a density, just like rho is a density of something.
Yeah.
Yeah. But you know, it wouldn't matter if it's uniform. It's the same no matter if you do the entire wire or a small bit of the wire. Okay.
Wait. Let me
Yeah.
listen.
No, fine. Yeah, I won't. But if these are electrons and they're moving this way, current, you can treat current as a vector. So I vector, in this case, this velocity is a vector.
Oh, 16.9 just cuts off this sides.
Yeah.
Instead
Oh no,
of,
mine does default to 4:3 then. Yeah, it's
Yeah.
because that's the size of the camera. Or something. It's probably not actually exactly that size. It probably doesn't let you use more of it. Actually, wait, what if square is the real size? Isn't it actually a circle? It is a circle. Camera is a circle.
no, square cuts off 4.3.
Oh, really? Oh.
So 16.9 also cuts off 4.3. So 4.3 is the actual camera.
Yeah, that's why they default to it.
Weird.
So the direction that electrons are moving, because electrons are negative carriers. So let's use a little example here. I vector equals rho times area times velocity vector. The charge distribution for the wire is negative for electrons, because electrons are negative. So the direction that the electrons are going is the opposite way as the conventional current. So conventional current is the direction that positive charges move in a wire.
Yeah.
Positive charges don't actually move in a wire, which is stupid. But this equation was made before we knew that. Electrons move the opposite way as conventional current. Current is always pointed as if positive charges are moving that way.
Yeah, so flow of electrons is the negative current.
Yeah. Although I guess you have to multiply. Yeah. So there will be like problems where you have to determine like how much current you have based on carriers, or what maybe the size of the wire was based on the velocity of electrons on the exam. They're kind of uncommon, but you do need to know carriers. And it's also kind of a good visualization of what's really happening with current. So much messier than last time. Oh well. So the electrons would be moving from the negative terminal to the positive terminal, but we draw conventional current as the positive terminal to the negative terminal. This is the way the current's going. And loops all have an inherent property called resistance. Resistance is the amount of impedance that the charges feel going through the loop. And in that carrier demonstration with all the velocities and stuff, the velocity of the electrons is regulated by stuff like the theory of relativity. They can't move past the speed of light, so they're going to hit some point. They're going to hit some point where it's going to be harder and harder for them to move faster because the actual definition of energy with velocity is not 1/2 mv squared. It's a little bit more complicated when you start reaching the speed of light. So that's partly contributes to the resistance of a wire. And then, I mean, you have that, and then you also have the size of the wire, and other things, which you can multiply into your current carrying equation to determine resistance. But anyway, the formula for resistance is, sorry, I didn't write it down. Oh no, I did. Resistance of a wire is equal to rho. Oh my god, another rho. It's
I thought
not.
it was V over I.
It's not. It's not
the
charge
same.
density. This is resistivity. Resistance is equal to resistivity
L over A.
times length over A.
The resistivity
Yay.
resistivity of the actual
wire.
wire material. Okay, of the wire.
That's okay. So that rho is just random. It's not significant. It's not a charge density. So if we take a wire and we double its size,
That's
it will have
not
4
L
times
over
the
A.
area, and then it will have 1/4 the resistance.
Wow.
If we double the length of the wire, then we'll have twice the resistance as this one. So if we have some wire, and this is like 1 ohm of resistance, and we double the length, now we have 2 ohms of resistance. And this is like typically a lot more helpful than the area. Like you're going to assign some like resistivity over, or resistance over length of a wire when you're like assigning a wire a rating. Like if you're buying wire, you're gonna have like some resistance over length ratio that you need to know about. Because it, like, if you have a really long wire carrying stuff, it will eventually decrease like the amperage rating of that wire because you can put less through it. It has more resistance. Okay, so actually in a circuit, there's a different definition of resistance, obviously, which is with Ohm's law. So the component that holds a lot of resistance is called a resistor. This is what it looks like for like the notation of a resistor, but you know in real life it's like a silly goofy thing. It's like sort of yellow.
Some of them are blue.
Some of them are blue, and they have like stripes with like some like code for like how much resistance it has. So a resistor
And
just
it matters which thing you put into which, right?
Why don't they just print the number on a through hole?
yeah, that'd be a lot easier, but they don't. Maybe it's cheaper.
Yeah,
Well,
it probably is.
the bands, once you know how to read them, it's easy to read.
Oh, on the
first of all-
resistors, like the pink and the red look exactly the same. It's really stupid, actually.
Well, first of all, they have to write both the resistance and also the how accurate it is.
Oh yeah, tolerance.
So one of the bands is
Oh, yeah.
tolerance.
Tolerance.
That's true. Yeah, no. As soon as you add tolerances, that
And it's definitely cheaper to
it's
put
definitely
like
yeah.
bands on them.
because then they have to put the actual material is just like isn't it? It's not. What is it? I don't know. Alright, continue the lesson.
Yeah. So the resistor has a certain amount of resistance, and that resistance is measured in ohms.
Oh yeah, decreasing construction costs.
Resistance is measured in ohms. Ohms is kind of its own unit. You don't really need to know exactly what the units of ohms are. It does have a unit value, but that's just to work with Ohm's law. But yeah, this is what a resistor looks like. This is how it's drawn on paper. And typically resistors are like what holds almost all the resistance in a circuit. Without a resistor, your wire will just make so much current that it's not helpful for most things. So we put a resistor in almost every circuit to make a certain current flow through that circuit.
Or you can just use a really small battery.
Not really. I mean,
Or
low voltage.
low voltage is the one.
Not exactly. You really can't because you need to be really precise. Typically, wires have such low resistance that it's easier to use a resistor. But
If you had like a 0.004 volt battery, that'd be pretty cool.
in the scenario where you don't have a resistor in a circuit, typically we just draw as if there is a resistor in the circuit, and we just call this resistor the resistance of the wire. So let's say this whole wire had a resistance of 0.01 ohms. This wire in like the drawing, a wire in a drawing of a circuit is treated as 0 ohms, and then we just call it a resistor of 0.01 ohms. That's representing the resistance of the entire circuit. Yeah, so wires are treated ideally as 0 ohms in a circuit. Okay, so Ohm's law. The relationship between the amount of current in a circuit and voltage in a circuit is V equals IR. If you double the amount of voltage, potential from 5 volts to 10 volts. And if it was already going at 1 amp, by the way, is the measurement of current. So an amp is equal to coulombs per second. If we doubled from 5 volts to 10 volts, we go from 1 amp to 2 amps. If we went from 2 ohms, I guess we already had, our volt was 5 volts, our resistance was 1/5 of an ohm, and we had 1 amp for this relationship to work. If we changed our resistor from 1/5 of an ohm to 2/5 of an ohm, then we'd have half the amps. 0.5 amps. 1 amp to 0.5 amps was 1/5 of an ohm to, oh my gosh, 2/5 of an ohm. This is all over the place. Okay, great. So that's Ohm's law. The amount of resistance governs how much current is in the circuit, and same with voltage. Cool. So in a resistor, here's a resistor. I'm actually gonna draw it out. Yeah, we got a resistor. Let's say we had a 220 ohm resistor. This is like a resistance value you might have in a resistor. And you're applying like 5 volts across the circuit. Let's say this is 220 ohms. Then you draw that there's a potential difference across the resistor. So because V equals IR, also delta V equals I delta R. I mean, that's not really significant change resistance. I guess we'll just write R. Delta V equals IR. So the voltage over here is 0 volts, and over here is 5 volts. This is ground, which is 0 volts. And this is positive terminal, which is 5 volts.
So the voltage drop.
Somewhere there was a voltage drop across the wire. So like it's 0 volts, 0 volts, 0 volts, 0 volts, 0 volts. And then over here, after the resistor, we have 5 volts, 5 volts. And that's because the resistor is what has all the resistance in the circuit. Yeah. So Kirchoff's rule states that the sum of the voltage drops is just equal to the total voltage drop. And
That's a couple laws though, doesn't he? Name
Yeah.
Kirchoff's law.
yeah, that's
Just
the,
like
that's
that's his first one.
the first one. That's
And
the
then his second one is like in the split of a.
yeah. We'll get to that in a second.
Then it's each one's equal or something like that. Each
And the
split.
sum of the voltage difference is equal to the EMF, the total electromotive force of the circuit. Okay. So let's say we had
The total what? The EMF is what?
Yeah, the EMF is equal to the sum of all the voltage drops. And all the voltage drops is equal to current times resistance.
Okay.
The current across an entire loop is always constant, but the voltage is changing.
So epsilon equals IR.
Yeah, sure.
Thank God.
So let's say we had a circuit and we had two resistors in the circuit. Let's say one was 1 ohm and one was 2 ohms. And then let's say we had an electromotive force of 3 volts. What would the voltage be at this point here? What would be the first step in solving this problem?
You mean for what the voltage?
The voltage at this point.
Oh, at that point?
Yeah.
Do we know the voltage of the battery?
Yeah, it's 3 volts. And let's also say that there's a current, sorry.
That looked like a question mark. Is that a 3?
Oh no, that's an epsilon.
Oh.
And we have a current of,
No, epsilon
Right.
equals question mark volts? Is that what it says?
that's a 3 volts, yeah.
Oh, that looks like a question mark.
Oh, my bad.
Okay,
1 amp, sorry. And we have 1 amp of current in the circuit.
what, it just drops 1 per ohm of voltage.
So
Right there,
first,
it's 2 volts after the first ohm.
on the ground, we have all 0 volts here.
There are 3, yeah, and then after the last resistor, it's all 3.
After the last resistance.
Oh wait, yeah,
all
because
3.
current's the not
Okay, so between them,
it's 1.
yeah, it's 1.
Yeah, it's 1. So we
Because
know
it
that
equals IR.
from here, the voltage difference is equal to IR. I is 1 amp. Resistance is 1 ohm.
Oh.
So we have 1 volt equals 1 amp times 1 ohm. By the way, these units end up working out. 1 volt here. And then as we go over the second one, so the difference in voltage here is 1 volt. The difference in voltage here is 2 volts because it's 2 amps.
Yeah.
2 ohms. Okay. So that brings us to the next formula, which is resistors in series. If we have 2 resistors in series, they can act like just one resistor. They don't have any other properties if we don't care about measuring the voltage in between them. So R net, which is the total resistance, is equal to R1 plus R2. Simple. You add the resistances together. And that makes sense because when we did like the length of the wire, remember we did resistance is equal to resistivity times length over A. So like if we have 1 ohm here and 2 ohms here, this is twice the length. You add up the lengths. It's like we added up the lengths of the resistors to get a higher resistance. Yeah. This is like resistor 1 is equal to rho times maybe 1 meter over A. Resistor 2 is equal to rho times 2 meters over A.
Resistors are just like curled up super thin wires though. Right?
Yeah, resistors are just really thin wires typically.
And they're
It's not
curled,
special
they like
materials.
spin inside them
Maybe they spin, I don't know.
to increase the length.
Probably do. So the resistance here would just be rho times 3 meters over A. So these formulas work the same way.
Oh.
And this helps because now when we're doing problems like that last one we just did, where we solve for the voltage in between 2 resistors, we can actually solve for the current ourselves. Let's go back to this problem. Imagine.
Oh wait, no, some of them are made of just like carbon composition.
Yeah, probably.
I mean, yeah, if you have a resistivity.
Oh yeah, no, look at
resistivity.
this stuff. Like, is it inside? They increase the length to increase the resistance.
Mm.
'Cause
Really?
It's,
I mean, they also decrease the area.
Well, yeah, that too.
So if we didn't know the current here, we knew there was 1 amp, or 1 ohm and 2 ohm, then we had potential equals 3 volts. We could determine the current here with Ohm's law. So V equals IR. In this case, it's V net equals R net. The total resistance here is equal to 3 ohms. So we know that I equals V net over R net. That's equal to 3 volts over 3 ohms. So that should be equal to 1 amp. Great. Next, we have resistors in parallel. But first, we actually have to learn Kirchoff's second rule, which is the intersection junction rule.
It splits in half or whatever. Or the one junction's equal to the other one. The
Yeah.
voltage. Or current. I don't know. I think
So
it's
Kirchoff's junction rule, is that what it's called?
Yeah.
States that the sum of currents in equals the sum of currents out. By the way, remember his other one was sum of delta V is equal to potential. So here, let's say we had 1 amp here, and we had 1 amp here, because it's the same loop. This would be distributed in some way along the 2 wires, so maybe 0.3 amps here, 0.7 amps here. That would just be based on the resistance. And then they come back and add up together to get that.
It's simple though, like makes sense.
It's kind of obvious, but voltage doesn't do that. You know, voltage and current are very different in that regard. Like voltage is like decreasing constantly, and amps are staying the same.
Yeah.
They're just different concepts. So if we have 2 resistors in series, I never know how many like humps to draw on my resistor. I should look it up. Can anyone guess what the formula is for R net of 2 resistors in parallel?
What? 1 over R plus R1 plus R2.
That's
1 over R1 plus 1 over R2. I mean.
1 over R1 plus 1 over R2.
I remember that.
You could also say that 1 over R net equals
Okay, well
1
yeah, that's
over
the
R1
that's the
plus
formula. you
1
said.
over R2. Yeah. Yeah, that's kind of weird. That's just the way it is. You can derive that.
And then it's series. In series, it's just R1 plus R2 plus R2.
Right.
Dot.
Right. So this is parallel. And R. What? How do I get that? Series R net equals R1 plus R2. So yeah, make sure you're using the right one, series or parallel here. Yeah. Okay. So capacitors. If we have a capacitor in a circuit, first we have our resistor, and next we have our capacitor. Capacitors have a certain amount of EMF in the circuit. So remember, we derived the formula for voltage of capacitor. We're not actually going to use the whole definition, but voltage is equal to Q over capacitance. The charge divided by the capacitance, because, so maybe we had 5 volts here, and maybe we had 3 volts here. This is like in the direction of the circuit. We're going this way. So we always have to sum up all of our voltage sources. The total amount of voltage here in the circuit would be 8 volts. If we add them up, you know, 3 plus 5 is 8 volts. If this was negative, then we have 2 volts.
As a capacitor.
No way. Yeah. capacitors can store charge in either direction. But yeah. The capacitor's voltage is also going to change based on how much charge comes in and out. And we're going to do a derivation for the amount of stuff in a capacitor based on the amount of charge. And charge is equal to the derivative of current is equal to charge. So we have a crazy relationship with that later. But anyway, for now you just need to know that they contribute a certain amount of EMF to a circuit, and it can also fill up and unfill up. But when we have capacitors in series,
Wait, so are lithium-ion batteries capacitors?
sort of. I think some batteries use like weird chemistry. They're all just like sort of a form of capacitor. A capacitor is just like an ideal type of storing charge that changes. Yeah, it's all about like a capacitor is defined by this equation. Like a capacitance, it has a certain capacitance value. The series for capacitors is actually the opposite of resistors. 1 over C net equals 1 over C1 plus 1 over C2. In parallel,
No, lithium-ion capacitor is a different thing
yeah, I mean, it's all like
from a lithium.
It's all really just
battery.
electrons and protons being pulled apart, or electrons being pulled from each other. In parallel, C net equals C1 plus C2.
That's pretty
Crazy.
simple.
And it's kind of cool because I explained like expanding the length of a resistor just makes the two resistor lengths add up together, and therefore their resistances add together. With a capacitor, you have like the same
Oh, it's the
thing.
opposite of the.
Yeah, it's the opposite. If we have two plates here, can you imagine we just add more plate? Because like when they're like in different circuits like this, it's like they're parallel to each other, just like a capacitor is like parallel in the way that a resistor is. I mean perpendicular. But if we add like the areas of the plates together, it's like these are just forming a bigger capacitor. That's why when they're in parallel they do that. And remember we have like capacitance is equal to what was it? D over kappa. Is it even called kappa? It might be called kappa. Epsilon naught area over D. It's like we're just adding the areas together, just like we're adding the lengths together with resistors. So yeah, capacitors in parallel and capacitors in series have the opposite properties, but really similar formulas to resistors in parallel and resistors in series. And finally we have power. So power from physics, mechanics, power is equal to du dt. U in E and M is just equal to QV. Therefore, du dt is equal to dqv dt. But usually it's not the charge that's changing, or usually it's not the voltage that's changing. If there is, you can use chain rule on this formula. But if it's just the charge that's changing, we have that's equal to V times dq dt, which is equal to IV. Current times voltage is equal to power. But if we had like a capacitor and that capacitor is changing voltage for some reason, then you could do some chain rule. So it'd be equal to dq dt times V plus dv dt times Q. But yeah, usually that's not happening. A battery, the voltage is staying the same. So the amount of energy flowing through a circuit is equal to the amount of voltage times the amount of current in the circuit. And that energy is all being dissipated somewhere else. When electrons are flowing through a circuit, here's the direction of conventional current. The electrons moving down the potential difference, all the energy is turned to heat. Or, I guess, sound in theory. Not really. All the energy is dissipated. And the power doesn't go anywhere else. So that's why, like, circuits with much lower resistances are more efficient. You want to minimize, like, the amount of resistors if you want to have power efficiency. Although, sometimes when you have a resistance, that means that you're doing something with that power. So finally, you can just substitute the equation for power into a lot of things. P equals IV, and then we know that V equals IR. If we substitute that, we also have power equals, we can just move this over here. If we substitute V over R into I, then we have V squared over R. If we do the other way around, we have I squared times R. And then we can also move this equation around. So resistance is equal to voltage over current.
Oh my gosh.
Current equals voltage over resistance. Typically people draw this triangle, which represents Ohm's law.
That was stupid.
V over IR. This is just saying that if you divide V and I, you get R.
Well, yeah, like if
If you divide V and R, you get I. If you multiply
well, it's
I,
saying like R equals V over I, because if you remove it, then it's V
Yeah.
is over the I, and then if you remove V, it's I. They're on the same level, but it's
Yeah,
stupid.
it's
You
kinda
can just
stupid.
you have the original function. You can just derive the
It's
basic division.
Okay.
Yeah, it's easy to remember these, though these are helpful. Yeah. So that's all.